Hello, welcome to Chem 125, Foundation Chemistry. Today, we'll be looking at atoms, molecules, and ions. In other words, the essential components of matter. Come along with me on this journey. You'll find this information in your textbook, Chemistry, the Central Science, Chapter 2, Atoms, Molecules, and Ions. To begin with, let's look at some of the key terms. Matter. This is anything the lungs is taking up space. And if we were to weigh you before and after you took a deep breath on a very, very sensitive scale, you would find that after you take a deep breath, you weigh a little bit more because you've taken in more matter. But what about my voice? Does it take up space? Does it have mass? Is it matter? Think about that one. Another key term is chemistry. And chemistry, at the broadest level, involves the study of the physical and chemical properties of matter. Things like boiling point, melting point, color. These are examples of physical properties. Being able to burn, how it reacts with an acid, how it reacts with air. These are examples of chemical properties. And when we study the physical and chemical properties, we also engage in study of the physical and chemical changes. All of this falls under chemistry. Now, when we talk about matter, all matter, anything that has mass and volume, is made up of incredibly tiny particles. These particles are known as atoms. Each one is an atom. And the atom is the smallest complete unit of matter. We'll be looking at that in more detail later. Now, when we take at least two atoms and join them together, we call that a molecule. So a molecule is essentially a group of atoms held together. The element is going to be the simplest substance in matter. It is made, of course, of atoms, as is everything else, but an element cannot be broken down into anything else. It is the simplest unit. And so we say that elements are substances which cannot be chemically simplified or broken down. But we can use elements and we can use them as our building blocks. So if we take two elements, react them together, then we're going to get atoms of each element bonding together. And when two different atoms bond together, we talk about having formed a compound. And that compound will contain atoms from at least two other or two different elements. And so when we look at matter, we look at it at the smallest level and then we build up. There is a theory behind the composition of matter, which we call the atomic theory of matter. And essentially it says that everything, every substance, everything that has mass and volume is made up of these simple building blocks. And these building blocks are called atoms. Now, the atomic theory of matter is based on work put forward by John Dalton in the 19th century. He based his theory on information and theories provided by other scientists. That's how science works, in that one person or a group of persons, they will study, analyze, conduct research, and they report on what they found. Others go through those reports and either build on it or look at it and say, well, no, that doesn't even make sense. And they move on to their own. And so in chemistry, it involves always looking at what was there, analyzing it, and then building on your own theory or following through with what's there and analyzing it. So when we talk about matter being made out of atoms, there are several different types of atoms, over 100, and these type of atoms are in substances we call elements. Right now, each of us is pretty much a bag of rusty, salty water if we look at the chemicals that make us up. And the water part of it consists of just two types of atoms, hydrogen atoms and oxygen atoms. When those atoms get together in a certain way, we make the water molecule, which has two hydrogen atoms and one oxygen. And so we see the hydrogen atom, the oxygen atom. Now, if we have a particular element, according to Dalton, all of the atoms would be exactly the same. So all oxygen atoms would look exactly alike. All hydrogen atoms would look exactly alike, but the hydrogen atoms would not look like the oxygen atoms. And in this diagram, we have an oxygen molecule. You recall that we said that molecules are where we have two or more atoms bonded together, linked together. So we have an oxygen molecule made up of two oxygen atoms. And we indicate that as O, the symbol for the element oxygen, and 2. The 2 is subscript, indicating that there are two of whatever came before it, in this case, oxygen. Likewise, we do the same thing for hydrogen, where hydrogen is usually found in molecules of H2, two hydrogen atoms bonded together. Now, when we have a chemical reaction, according to Dalton, the atoms are not themselves broken down or changed into something else. What happens is that the atoms get together to form the new substance. But that new substance contains all of the atoms that we put in to make it. So that when we talk about water, and in this case, they're showing water here being split using electricity, the water molecules are composed of oxygen atoms and hydrogen atoms. And so each water molecule contains one oxygen and two hydrogens. According to Dalton, the atoms of an element are not changed into atoms of a different element by chemical reactions. So we can summarize to say that atoms are neither created nor destroyed in chemical reactions. According to Dalton's postulates, when we have the elements combining, we form a compound. And a compound always has to have at least two different types of atoms, at least two different elements. Going back to our simple substance, water, no matter whether it's Aquapure, Lutrapure, water from the government tap, water from rain, all of this water contains one oxygen atom per molecule and two hydrogen atoms. So all water contains oxygen and hydrogen together in a molecule. And the number of hydrogens for every oxygen is going to be 2. So we can say that a given compound always has the same relative number and kinds of atoms. No matter where you get your water from, whether it's alkaline water, low salt water, spring water, the water component of it will always have a ratio of two hydrogen atoms to one oxygen atom. This is known as the law of definite proportions, and this was stated by Joseph Proust. So that the composition of a pure substance is always going to be the same. So, for example, I'm sure that in your kitchen, you're likely to have a salt, sodium chloride salt. And for sodium chloride, that's the salt that you season your food with. For every sodium unit or atom, there will be one chlorine unit or atom. The ratio of sodium to chlorine in sodium chloride will always be 1 to 1. So if we take the example of water as a pure substance, H2O, we take the example of sodium chloride as a pure substance, NaCl. It doesn't matter where in the world you got these substances from, those particular compounds will have the same proportion of element 1 to element 2. And that is the law of constant golden special or a conch snack. And let's say that conch snack, if you were to put it on a scale, it weighed 15 ounces. Now, just before you ate the conch snack, you would weigh whatever your weight is. Immediately after you ate the conch snack, how much would you weigh? Well, if the conch snack weighed 15 ounces and you ate the entire conch snack, then your weight after you ate it would be your weight before you ate it plus 15 ounces. Why? Because the total mass of substances must be the same before and after. And as you move through the day, you would start burning calories, using up some of that conch snack. And so the weight, your weight would go down. But as your weight is going down again, you are releasing substances to the environment. You are breathing out air that contains carbon dioxide and it contains water vapor. And that water vapor, that carbon dioxide, some of that has come from breaking down the conch snack. If we were to collect everything you released, whether it was carbon dioxide, water, your urine, your feces, and keep everything together, then the mass of what you started with would equal the mass of what we collected. Well, that is true for any chemical reaction or set of chemical reactions. What goes in must be traced, must be trackable, so that even though you change the substances from A and B separate to A and B combined, the total mass must be the same. And we call that the law of conservation of mass. So the total mass of substances present at the end of a chemical process is the same as the mass of substances present before the process took place. And essentially that means that whatever amount you put in, that is the mass you're going to get out. It may be transformed into a different state, into a different compound, but the total mass is going to be the same. Banks work on the same principle. If I put $10 into my bank account today, and I was the very next day, all I can get is 10 because that's all I put in. If I took out 5, then I expect the bank to have 5 left for me because they're not supposed to make my money disappear. Money that goes in should come out. Now we know that the banking example isn't quite exact because there's interest in bank fees, but you get the idea. When a chemical reaction takes place, the total mass does not change. So the mass of substance you put in equals the mass of substance you get out. That is the law of conservation of mass. And so, with these laws in mind, and with the information on substances being made out of atoms, a number of studies were done to explore the physical properties of matter and to define, well, what makes up an atom? Now, J.J. Thomson did a number of studies, and what he found was that when we passed a gas through a certain setup, and within the setup, we have a high voltage current going through, we have a fluorescent screen, which is going to collect material or detect material, and we have a magnet. So we're passing electricity through, we have a magnet. Now the magnet provides a source of attraction. We also have a negative plate. So we have a positive zone, we have a negative zone, and we have a magnet around this glass tube. And what he found was that when he passed material through, some particles got pushed or sent in a certain way. And what he had an hypothesis was that, you know what? There are particles that have a negative charge coming out. And because they have a negative charge, they're going to be pulled in a certain way. Do you think they were pulled towards the positive plate or the negative plate? I'll give you a hint. Opposites attract. And so when he devised the cathode tube, what he found was that there were negatively charged particles coming out. These negatively charged particles were directed towards the positive zone. So that's J.J. Thomson and his contribution to our understanding of atomic structure. Now, Thomson also measured the charge to mass ratio. In other words, if I have a charge of 1, how does that compare to my mass? Is it that I have a charge of 1 for every unit of mass? Or is it a charge of 1 for every 2 units of mass? Or something like that. And what he found was there was 1.76 units times 10 to the 8 units of charge, represented in coulombs per gram. Is very large. Takes a substance and divides it into very, very small particles. You can almost call it just a spray. And a squirt of gas was introduced into a container. And again, notice that we have a positive plate and a negative plate. And so we're spraying particles in. And what was done there was to determine or to look at the charge and mass again. So we're actually able to look through. We have ionizing radiation, and we have the plates again. We have the positive plate and the negative plate. And using this information, as well as the work of J.J. Thomson, Robert Millikan determined the actual charge on the electron in 1909. Now, you recall that what J.J. Thomson did was he looked at the ratio. In other words, compared to the size of the electron, which is very, very small, the charge was large. He didn't identify or quantify the charge. He just looked at the ratio. Millikan, however, wanted to determine what is the actual charge on an electron. And so in 1909, he did this work using the oil drop experiment and used that to determine what the actual charge was. Another contributor to our understanding of atomic or particles. And so radiation is something that's occurring naturally around us. It's a spontaneous process whereby particles are releasing energy, releasing particles. And here we have the work of yet another scientist, Rutherford, Ernest Rutherford. Now he looked at radiation, and in his studies, what he did was he took a radioactive substance. Remember, I said that there are a number of substances that are naturally radioactive, and he put it into a lead block. Now, the beauty of a lead block is that lead essentially prevents radioactive materials from escaping. And by putting it into a lead block with a channel, what he did was force the particles, if they're going to come out, they could only come out in one direction. So we have the lead block, we have a channel whereby the particles can come out. They can't go around here because of the lead. And so they come out this way. He then focuses that path, and here we have this. We have a piece of material with a small hole, which forces that radioactive beam to go through. We then have, again, electrical plates. We have a positive plate and a negative plate. And the purpose of these is that they are going to tease apart the particles. A positive charged particle would be repelled or pushed away by the positive plate. A negatively charged particle would be pushed away by the negative plate. A particle that has no charge would neither be attracted or pushed away by either of those plates. So let's have a look. The blue represents the complete stream of particles. We pass the stream through an electrically charged zone. And what Ernest Rutherford noticed was that some particles were pushed rays. Some particles, as they pass through, or one part of the beam was pulled down. In other words, being pushed away from the positive plate and being drawn towards the negative plate. And so by passing this beam from the radioactive substance through a focusing material with a hole in it, and then through the electrically charged zone, positive plate, negative plate, Rutherford found that he could separate the radiation into three different rays: beta, alpha, and gamma. And those were captured and recorded on photographic plates. Now, around 1900, there was a theory that an atom was kind of like a plum pudding. Well, we in the Bahamas don't really do the plum pudding kind of thing, but what we do, some folks, they like fruitcake. And with fruitcake or with raisin bread, you have the raisins, the fruits, kind of scattered haphazardly throughout the structure. Well, a plum pudding is kind of like that. whereby you have bits of fruit, maybe even some nuts, and they're scattered throughout the whole pudding structure. Or in the case of fruitcake, scattered throughout the whole structure. Or in the case of chocolate chip cookies, my favorite, like the chocolate chip, they're not all sitting on top, they're not all sitting on the bottom, they're scattered throughout haphazardly. So that was the theory around the 1900s, that the particles that make up an atom, they're like all over the place, random, haphazard. You had some positive charges, you had some negative charges all over the place. Now, you recall that Rutherford had done some studies and he looked at alpha, beta, and gamma coming from rays. He was really curious about these particles. And so, in another experiment, what he did, we had a source that he found released alpha particles. And what he did with this was he had this release going on, and the particles he found, some particles actually just went straight on their merry way. They were not deflected in any way by this piece of gold foil, but a couple of particles got bounced way off path. So he's passing this beam into the gold, and some particles, they're like, hey, gold on the left, gold on the right, don't mind me, I'm going straight. But other particles, they're like, whoa, gold, and they bounce off it. And so Rutherford was like, hey, what happened there? The particles are scattering. What could cause that? And so he thought about it. Why are these particles mostly going through the piece of gold, but some of them getting knocked way off path, almost as if they're hitting and bouncing somewhere? So some particles were being deflected at large angles. What does that mean? It means that Thomson's model could not be absolutely correct. You recall J.J. Thomson. So if some are being deflected, it means there must be something in there that these particles, the alpha particles that he was shooting in, are hitting something and bouncing off. What are they hitting? The nucleus. And so if we look in detail, zoom in on the gold, then most of the particles were going through because most of the atom was just space. But if the alpha particle hit the nucleus, which is a dense zone containing particles, which we'll talk about later, then they got deflected, they got bounced back. It was like they hit a wall. So most of the particles are going through essentially empty space of a gold atom, but when the alpha particles hit the nucleus, they bounced off because they encountered something that was dense, solid, and they got hit in a new direction. Well, if that's the case, what Thomson proposed could not be correct. So let's see how we grew from this. So Rutherford, based on his studies, said, you know what? Even though we have the atom and most of my alpha particles pass through, there had to be something that was inside the atom that was very dense and causing my alpha particles to bounce off. And so he postulated, he proposed, he said, there must be something that's very small. Why very small? Because most of my alpha particles missed it, so it must be small, but it must be dense so that when I do hit it, I get that big deflection. So for Rutherford, he said, well, most of the atom is pretty much empty space. That allows the alpha particles to go through. But somewhere is a dense nucleus. And so here we see the concept of a nucleus being a place that has the particles being proposed. Now, Rutherford also went on in 1919 to discover protons, and James Chadwick in 1932 neutrons. So we now have protons, neutrons, and electrons. These then are the subatomic particles. These are the particles that make up every single atom, that makes up every single element of every single substance that has mass and volume. In other words, all matter contains these particles. The particles are protons and electrons. These two particles have charge. The protons are positive, electrons are negative. Protons and neutrons, these are going to be the larger particles. They have a mass that is almost the same, slight difference in them, but not too significant. But their masses are about the same. Electrons, on the other hand, are so small that for most you're walking down the street and you look down and you see a glitter and there's a 5-cent coin. Whoa, it's money. Well, now consider that you're absolutely broke. You have no money. You found a 5-cent coin. Are you going to call your friends? Whoa, I found some money. I'm rich. Or are you going to still be essentially broke? I mean, you have the 5 cents, but are you going to go over to McDonald's, Wendy's, Burger King, Salad Master, Kentucky, the food store, and go in there like, yes, I'm going to go buy lunch? I don't think so. So now what if you'd found $100 bill? Yeah, you'd be balling. You can go and have lunch that day and have money left over for the next day and the next, and so on. So even though in both cases you have actual money, the 5 cents, you can say, well, bruh, I'm broke, because the 5 cents really isn't taking you anywhere. But with $100, you can get lunch. You can get lunch, dinner, breakfast, all over again. So that is to say that even though we're ignoring the mass of the electron, it actually does have mass. It's like the 5-cent coin to a broke person. It's almost nothing, but it has mass. But when we look at the protons and neutrons, they're like the $100 bill. Their mass is so much greater than that of the electron. So subatomic particles, we've seen the background as to how we got to know about them. There's a proton with a positive charge and an atomic mass unit of approximately 1. There's a neutron and the neutron. That is the end of unit lecture 1. Be sure to review and also go through the additional information provided to assist you. Thank you.